W1. Alright? Then copy this one. Copy. Can paste here. No. Asking too much here. Okay. So let's see. F, we still don't know, that's the fanning friction factor. G, that is just M over S. Alright, no problem. V bar, what is it? I thought I said it earlier, a few slides ago. Alright, this one. WVG. Okay. WVG plus 1 minus WVL. Alright, G is fine. VLG is VG minus VL, is it? Here. VG minus VL, correct. Alright, dW dx, well, W, not dW dx, but just W alone is M gas over M liquid. Is that right? Is that correct? W is the quality, okay? G, well, that normally is 9.81. Sin theta is the angle of the pipe. The pipe like this. This is theta. Okay? This is pipe. Okay? V bar already same. Okay? V bar same this one. G, W, dVG, dP. Well, that form. PV, if you assume PV equals to RT, then dVG on dP is equal to, what was that? Minus RT over P squared. Right? Ideal gas. Okay? Normally, the liquid one we neglected because the specific volume of liquid is more or less constant. Doesn't change with pressure. Very minor change. Whereas the gas has a major change there. Right? Okay. Everybody okay so far? Now the big problem here is, number one, finding that fanning friction factor. Number two, this one is dP dx. We can calculate it at any point in the pipe. But if you go down further along the pipe, as the gas expands, contracts, all sorts of things, the whole thing will change. I don't know. Okay? Which one will change? Oh no, W won't change, that's okay. Oh, W will change. Oh no, W won't. That's okay. Fanning friction factor might change. Alright. If it's boiling or condensation, the dW jet, that will change. VLG will change. Sin theta is fine. Actually, the problem one, it would be here. As you go down the pipe, okay, as you go down the pipe, the pressure will change, and therefore this term will change. This term looks like it changes, isn't it? Because the pressure change, this one will. Alright? So this causes a problem. So the integration doesn't work out that easily. Okay? One strategy is let's say you want to work out on a 2 meter long pipe. you could break it up into small segments, all right, and assume it varies linearly along each little segment and then add up the effect. I think that's what we do in the tutorial question. All right. So it's not like you can just plug in our numbers all in here and come out one go. You actually have to do for the first segment, calculate what, let's say 2 meters. How many segments you want to break it up to? It's up to you, but the more segments, the more accurate it will be. All right. If you break it up into, let's say, 5 segments, so after the first segment, all right, work out what the pressure there is. All right. Work out the conditions there, and then use that to extrapolate the pressure drop in the next segment and so on. And then add it all up together. Does that make sense? All right. So that is basically the 2 things that we will do in this tutorial. Number 1, estimate the friction factor, which I'll talk about now. And then number 2, when we apply it, we need to also adjust for the what do you call it? For the variation we need to do it in segments, because you can't do it in one big step. It won't be accurate that way, because these numbers are changing within the pipe. It's not a constant dpdx like the rest of the course. Okay, let's see here. Okay. No, I thought. Okay. Oh, this one is for pressure change small. So sorry, I was looking for terms. We can only use this if the pressure variation is smaller, right? But I think that in that case, the pressure variation not small. But let's see. All right. Now, as I said, first I'll describe the friction factor. All right. This F fanning. One way is just to assume it's 0.07, a typical number. Okay. But if you want to be more accurate, let's see. All right. Then there's this other problem here. All right. We first assume it to be single phase. All right. If we assume it to be 100% liquid, we can find the pressure drop for the case when it's 100% is liquid only. The subscript LO. All right. We do that the same way that we did for the pipe flow. All right. The only thing is we use the Moody chart. Make sure we get the Darcy friction factor, you divide by 4 to get the Fanning friction factor. All right. So what we do is we assume liquid only. All right. We can find the pressure drop how we normally do. Calculate the Reynolds number. Liquid only. All right. And look up the chart. After that, you can for the relative roughness, you get a Darcy. You divide by 4, you get a Fanning. After that, you can work out that one. All right, liquid only. Okay, and we assume the Fanning friction factor. All right, by dividing the top 2 equations, this one, that one divided by this one is equal to that one divided by this one. I think most terms cancel off except d bar over VL, F fanning over FLO. Right? So that way we can estimate I got two there. Alright. Okay? Yeah. So this F fanning over FLO, okay, yeah, 1 and 2 here. So if you are assuming it is 100% liquid or more or less, then we assume the F fanning over FLO is approximately 1. Okay, that's just a guess. And this d bar over VL is expanded there. D bar over VL, and then so the dpdx for the fanning equals this times the dpdx for the liquid volume. That's the correction factor. Okay, so this is a correction factor. All right. If we did the same for gas only, I think it's exactly the same. All right, except the here we have V bar over VL, and only that thing changes. Okay. So that's the correction factor or the two-phase multiplier. This term that we found just now. Right, dpdx of the system is some correction factor times this liquid only, or this equals that times gas only. Okay. All right. Okay. All right. I think this one is added extra material. If you don't want to believe it's all liquid only or gas only, then we need to work out some sort of average viscosity, all right, and then look up the Reynolds number, and then look up the friction factor for that Reynolds number based on our average values. All right, different ways of finding the average. But again, we won't use this one. This one's more extra. All right. So I think now let's try to implement that we just did in here. Where is it? Where is it here? No. No. So okay. Okay. We'll try to do question 4 now, which basically try to estimate the friction factor. What is the value of the friction factor assuming isothermal condition? Okay. So air flow rate quite high, you know. Alright. This one air flow rate quite high. Normally air flow rate not so high. I would tend, most cases, we would do liquid, treat as liquid only. Alright. Okay. So, anyway. So, wait. No, I don't need this anymore. Let's save. G squared. Okay. So G is ML plus MG. So that is 0.08 plus 0.32 is 0.4 kilograms per second. Is that okay? Right? G is the total, isn't it? Okay, G is no, sorry. Sorry, G is M over S. Alright, over S. Over S. S is what? S is pi d squared on 4 pi 0.025 squared on 4 kilograms per meter squared second. Mean pressure 9.9 bar. I think we need to find all the specific volume first. No. We need this one. They give already VG, VL. V bar is equal to what is W? M G over ML. Is that correct? ML over MG? Oh, divided by MG plus MG. Total. Is that right? Okay. So MG is 0.08 divided by 0.40 equals 0.2. Right? Has anyone worked out what G is? 814. 4.9. Okay? Alright, so this one, VG given, VL given, so you can work this out. It's not a lot of air, 20% air. Alright, have you worked out what V bar is? Yeah. 0 point, huh? 0.174 meter cube per kilogram. Alright. Okay, so here, this part, here it goes. Alright. I'm a bit skeptical, but I think normally we choose that 100% liquid. Alright. So to find, first we find FLO. Alright. We calculate the Reynolds number for assuming it's liquid only. I think this is rho V is rho V is equal to G. Is that correct? Alright. Okay. If rho V is equal to 1 over rho U lah. Rho U 1 over V, the specific volume, times V is actually G over U is actually M over S. Alright. And this is equal to G, is that correct? Mass M is that correct? No. Oh, sorry. Q. Q, sorry, Q. Is that correct? Alright. This is equal to Q over V over S. Specific volume. G is M over S. Yeah, correct. Is equal to Q over V over S is equal to M over S equal to G. Alright? Q divided by specific volume is equal to rho Q. Alright? V is specific volume. Alright? Is equal to rho Q over S is equal to M over S is equal to G. Alright? So it's correct. Alright? So Reynolds number RE equals to rho U D over mu. Alright? So for rho G, for rho U we take G diameter over mu. This mu, because we are assuming liquid only, so we take that of liquid. So what is G that we found? Why are we finding G over S? This is G, isn't it? Right? M over S. Okay. So 814.9 times diameter 0.025 over, what is this? 1.2 by 10 to the minus 3. Alright? Okay. What's the Reynolds number? This is RE, liquid only. Alright. Sorry if you're a bit confused, we are following this method here. We are assuming 100% liquid. This per system, no. Oh, sure. Alright, we are assuming 100% liquid. We are using this way. Alright. Okay. What's the answer? 16977. Huh? Okay. Okay, so then we look up the Moody chart. F Darcy equals. Everyone following so far? This calculation is just, if you're confused about this calculation, this is just to show that rho u can be replaced with G here. Alright. F Darcy, save this one. Goes one. So many. Okay, Moody chart. Okay, I think for this problem they didn't say, so we assume smooth pipe. 16,000. Is it 16,000? 17,000. Is it 17,000? Okay, 17,000. So here's 1,000, 10,000, 20,000. Yeah, so 17,000 about here. So about 2.7. 2.6. 2.6. 0.026. Okay? Alright? So F Darcy is 0.026. F Fanning is 0.026 divided by 4. Right? What is that? 0.0065. Okay? Okay. But that's not the end. This is F Fanning, liquid only. Alright? Okay, do I use that one or this one? Do I use that one? Or? Missing something here. Doesn't say, yeah. All right. We can, where are we? Here. All right. So now that we have this factor, we can calculate the pressure drop for liquid only. All right. And we can also calculate this correction factor. So we can actually get the pressure drop for the combined system. All right. But this question is a bit strange. They ask for the friction factor only. So do I go back and calculate that one? I don't know. I don't know. That's a bit, because from here you already got what you wanted, the pressure drop due to friction. But then you go backwards and calculate that one. But if that's what the question asks, then we do it. It's a bit straight. So I'm not sure whether. All right. I think I'm correct. Okay. All right, but just a bit strange that you go back and calculate the Fanning friction factor or the friction factor since you already got it. But anyway, let's do that lah. Okay. So next one, we use this one. Okay. dP on dx, liquid only, is equal to minus 2 FLO G squared VL over DI. Minus 2 G squared F liquid only. Forgot. VL over DI. VL over DI. Okay? So equals to minus 2. What's G squared? 814.9 squared. 814.9 squared. FLO is 0.0065. VL is, what is VL? Is in your question, isn't it? Huh? 1.02 times 10 to the minus 3 over, what's the diameter? 0. Is that right? Okay. Once you've done that, the next step would be to calculate the dP on dx for the system. All right, for the multi-phase system, I think they put F equals 1 plus dg over VL minus 1. 1 plus dg over VL minus 1. W. There's a W here. All right. Multiply by dP on dx, liquid liquid only. What's the answer? Yes, it's negative. Pressure drops. Negative 352.21 Pascal. Okay. So for the combined system, this is it. So 1 plus, what's the W again? 0.2. Vg over VL. Alright, minus 1. What's Vg? Here we minus 352.21 Pascal. What is Vg? Huh? It's given. I presume you copied it down. 0.28. 8.28 times 10 to the 32. VL? 102. Okay. Alright, so you get the answer there. And finally, dp on dx of f equals to funny on it, minus 2 ff minus 2 ff g squared v bar over di. Alright. What's the dp dx, this one? What's the answer here? It's not minus, multiply. Huh? Oh, this one is 6K, so big. Alright, and then if you put it back in here, what do you get? Strange, huh? How come mine different one? PV equals to RT. Actually, my own. What's the answer? 0.0065. Same. Okay. Actually, this part here is wrong. It's not supposed to do like this. Okay? Well, alright. Everybody okay with this one? Alright? So it's a bit roundabout way. I'm not sure whether. I think that's what the question asked for anyway. Alright? Sorry, my earlier mistake. So, this one, PV, or the gas, equals constant. Alright? By right, I doing the other way is wrong. It's like what you're actually supposed to do is P dVg plus V dP, alright, equals to 0. Constant. Alright? The rate of change of this. So use the chain rule. And then, therefore, you get P dV equals to minus V dP. Or, in this case, what we wanted to do? What we wanted, dV dP. dV on dP is equal to minus V over P. Is that correct? Alright? Yeah, I remember there was no P squared around. I think that's wrong. Alright? So dV dP is actually not minus RT, this one. It's actually minus. Okay. Alright. The second, well, 130 here. Okay, the second problem, actually there's an example problem in the notes here. Okay, So where? All right. Maybe we just have a quick go through this one, then we get a better idea, so we won't mess up the tutorial problem. All right. So this one is similar to that problem. The mass flow rate of air is very low compared to water. All right. In a vertical smooth wall. But now, okay, now we want to look at. Just now we just calculate the friction factor alone. In this case is the whole pipe. All right. Not only this term, but we want to look at all the other terms also. All right. So air and water. This case, yes, very clear. The m dot of liquid is a lot bigger than air. Upwards in a vertical smooth wall tube pipe, the diameter 20 and length 1.3. Using the homogeneous flow model, calculate the pressure drop across the tube, negative any effects. The fluids are at temperature 20 degrees. Expansion air can be assumed to be isothermal. Right? So PV equals RT, R the temperature isothermal. The exit pressure is 1 bar. Right? So I have to calculate pressure drop. So this is the equation that we need to use. So there is no change in quality. So first this term can drop out here. All right. Then the following values are quite easy. So S is the area, M, mg plus ml. I think G. All right. We can calculate G. We done that just now. Can calculate the W. No problem. All right. For isothermal expansion, dVg dP is minus Vg over P. So for thermodynamics table, density of air, so is that, so dVg over dP is that, all right? So Vg is the density of air, 1 over the density of air divided by pressure. You get this one. Okay, so this value here, all right, is this one. For Vg is 1 over the density of air divided by 101 kPa, I think. 1 atmosphere. Try to see where you get that, no? Punch that in calculator. 1 divided by 1.19884 and divide again by 101 thousand. Do you get 8.455 and 10 to the 6? About that, eh? Is that correct? Okay. So everybody's happy that one? Okay. So G squared omega dV, this one. All right. They just put the numbers together. This is for the denominator here. All right. And what they do for friction factor? Okay. For friction factor, this term, they assume liquid only again. All right. All right. Find the Reynolds number. Look up the LO. All right. Moody chart. And then they work out the pressure liquid only. And then they multiply the correction factor. All right. And then they get the pressure drop. All right. And static head. And then they put it all back in the equation. And they get that. Okay. All right. Is that too fast? All right. Okay. All right. Let's try to do that. All right. You can go through this on your own, but let's try to do this one with the tutorial problem. Then you can see how how it works. It's actually exactly the same problem, only numbers different. All right. So let's do that one. Okay. Okay. Okay, this one. Okay. All right, and we need this equation. Okay, so basically this is a pipe like this. The stuff goes in here, comes out here, P atmosphere. Here P is something which is would expect to be higher than atmosphere. All right. Again, the first way, all right. What we are going to do, we calculate it in. We assume the pressure change is small, and we do it one big step. Okay. We assume that dP dx is constant. We calculate all these terms, and then we just multiply the dP dx multiply with what is multiply with the length. To get the pressure drop, we just say delta P over L, and we just multiply this term with the length. Is that right? Okay. But actually, we do that first. But actually, that's a very crude way because we expect a large change up. Alright, but we do the simple way first, and then I'll explain how you would do the complicated the other way. Alright. So actually, this term, alright, this is the dP on dx f, alright, which we can calculate separately. Okay. Alright. This term, this one is 0. Okay? 0. This term, no problem. Sine theta is 90 degrees. So, sine theta is 1. Okay? Theta is 90 degrees. Alright? No problem. So, let's see. Okay? V bar. What is V bar again? Huh? VL plus 1 minus omega. Is that correct? Omega Vg. Oh. Okay. Alright, so this is what air and water. So we assume what is omega? So we need omega first. So sorry, omega is equal to mg over ml. This is what? 4 by 10 to the minus 3 over 1. Is that right? Correct. Omega is the quality, isn't it? Huh? Oh, divided by 1 doesn't make any difference. Sorry, m. So it's 1 plus 0.4 times 10 to the minus 3 equals, I think it's around 0.004, isn't it? Okay. So Vg is equal to 1 over rho of air. At atmospheric pressure, we take 1 over 1.23. All right. VL is equal to 1 on rho water, and that's about 1 over 998. Okay. Then that you can find that one. G sine, okay, G squared. G squared, G is what? m over s. Yeah. M is what? 1.004 over, what's the diameter of the pipe? 40 mm by 0.04 squared over m over s, area, by d squared over 4. dVg over dP is equal to minus Vg over P equals to minus Vg 1 over 1.23 over pressure 101,000 approximately. Okay, so with that we actually got all the numbers. We can, the only one we don't have is that one, so we'll do that after you done this part. The other method easier. I don't know why they switched back to this one. What is D bar? 4.25 times 10 to the power of negative 3. Okay. What is dVg dP? Huh? Minus 6. Is it 8 point something here? Huh? 8.05. Okay. This one? 7.98. 7.99. 7.98 is it? 798. Just put 799 lah. 799 kilograms per meter square second. Alright. Is that okay so far? Alright, so the only part here that we haven't, so we can put in all the numbers, no problem. Alright, the only part we haven't done is this one, therefore, but we did it just now, we have to do it again. Alright, this term is actually your dP dx F, isn't it? Okay, and this case is close to 100% liquid, so that's fine, isn't it? Alright, so we need to find this term. To find this term, it's actually this correction factor times this term. To find this term is here. FLO here. So we follow our same procedure we did just now. Alright. So the first step, we calculate our RELO is equal to G D over mu L. G D over mu L. So G is 799. D is 0.40 mm, is it? Over mu L is 1.2 times 10 to the minus 3. Alright. This one in this case, the roughness is 0.025, 0.25. E over D is 0.25 divided by 4. 40. 40 equals to what? Then after that we look up F Darcy. FD equals to what? F Fanning equals to FD over 4. What's the Reynolds number? Huh? 26,000. 26,600. Close enough. Right? What's the relative roughness? 0, 0? What? 0, 0, 6. 625. Okay? Alright. Can I switch to Moody chart now? Alright, you all okay? Huh? So switch to Moody chart. Where are we just now? 26,000. 20,000, 25, 30, 35, 40, 20, 25, around here, huh? Halfway here. 006. 006 here. 006 Hey? Double 06. Are you sure so big 0.25 divided by 40. 0.06. Okay. 006 is up here. 625 6 and a bit here. Alright. So Fanning Darcy friction factor is 0.03 03315 no, this is 3, 2, 4, 6, 8, 10. 3, 2, 3, 3 Alright, 0.033. Is that okay? Alright, all agree? And most agree is okay. Yeah? Wrong I read wrong sorry. I read here. Mistake. 26,000 is it? So it should be here. 10,000. 26 should be here. Oh, 6. Alright, so Fanning friction factor is around. Oh, one. Repeat again. What do you mean one line below? Oh, sorry. Should be here. Okay. So 335 like that. 0.0036. I think more like 5, right? 2, 4, 6. It's right in the middle. 035. Okay? Okay. Alright. Okay. So F, this one is 0.035. So remember, you need to divide by 4. What is that? 8. Is that 875? 88. Okay, 0.0088. What is supposed to do next? Okay. dP dx LO. dP on dx LO equals 2 FLO G squared DL over DI. 2 FLO G squared D over
DI. G squared VL. Is that okay? So that is 2 minus 2 F LO 0.0088 times G squared. What is G squared? 799 squared. 799 squared. What is VL? VL 10998 over DI 0.04. Is that correct? Okay, so that's your dP dx at liquid only. Then after that, what else? That's the correction factor. dP on the F equals to VL. Huh? V bar is this one here. We are doing this one here. What's the answer? Huh? 281.5 negative. Alright, dP dx F is equal to, what's the correction factor? 1 plus W. 1 plus W Vg over VL minus 1 minus 281.5. One plus W. W is what in this case? 0.004. VL, this one be 998 over 1.23 minus 1. Minus 281.5. How many Pascal per meter? Is that correct? Vg is 1 over 1.23. VL is 1 over 998. So it comes like this. What's the answer? Huh? 194. 1194. Negative. Okay. Okay. So the final step is to put it all back in here. Okay. Minus dP on dx is equal to this first term, all right, is minus 1194. All right. Second term is 0 plus 0. Third term is G, all right, with 9.81. What is V bar? V bar is 4.25 times 10 to the minus 3. 4.25 times 10 to the minus 3. All right, bottom term, 1 plus G squared W. 1 plus G squared is what? G is what? 799, is it? 799 squared. W is 0.004. dp dx is what? Or dvg dp is what? dvg 8.05 times 10 to the minus 6. 8.05 times 10 to the minus 6. Is that okay? You saw all that, okay? So this problem, if you do and you want to do check, you can, the problem done in the text, in the notes, exactly the same, just the numbers are different. Alright? Sorry, there's a mistake here. Where's this thing? Come on. So, dp dx of f is equal to minus of this one. But the term in here is only positive. There's no minus here. So, actually, here should not be a negative. Okay? Because the negative already on this side. Right? It's already minus dp dx equals to this one. Right? So this one we cannot minus it again. Right? So what we worked out just now, this term that we worked out just now here, this is actually minus what? 2ff g squared v bar on di. But the term here is what we want is not minus, but we want 2ff g squared v bar on di. That's why there's no minus. Is that okay? Alright. The term that we worked out was actually minus. It's minus 1194. But the term in here is not minus. There's no minus. So you drop the minus sign. Is that okay? Huh? dvg dp is minus. Yeah, it's negative, sorry. Yeah, it's negative. So, this one should be negative. Minus 8. Okay? The gravity dp dx. Okay, correct. What's the answer? Huh? 3575.7 Pascal per meter. So, what? Last comment here. For pressure, all right, it says it's a 2-meter pipe. If you assume like this, delta P over L is equal to 3575.7 Pascal, we will get delta P is equal to, what's this times 2? It's a 2-meter pipe, isn't it? What's the answer? 7 something, is it? 751 Pascal. Okay? Alright. But Pascal. Okay, maybe not so big. Alright? Okay, you can stop writing now. Yeah, well. Just listen one last minute. Okay, have you all done up to here? Have you all reached here? Okay. So the last comment I have, no, here. By right, this pressure we put in here 100 kPa, but the pressure is changing. The pressure at the end of the pipe is 100 kPa. So it's a vertical pipe. The pressure at the end of the pipe is 100 kPa, but the pressure at the bottom of the pipe is 107 kPa, according to our estimate. All right, it's higher. Okay, so by right, we putting one value here is not so correct. Okay, now number one. All right, number two, the VL here that we use, where here? Okay, the VL is correct, no problem. 998, even at 100 kPa, 107 kPa, 998 is correct. But the VG that we use, 1.23 also assumes at 100 kPa. If it's at 107 kPa, it will be slightly less. Alright, is that okay? So, not correct. Alright. Which other things? I think everything else looks okay. Alright. But if you want to be more accurate, the notes, where's the notes? I think here. Okay. They did for their problem and they just got a value there. Alright. But we won't do this. I think you're all very tired now. Alright. But to be more accurate, instead of doing it one step, they broke the pipe into 5 segments. Alright? And then I think here 5, segment number 5, at the end of it is 1 bar. Okay? So they work backwards. Alright, segment 4, 3, 2, 1. Whereas the pressure, because the pipe at the outlet is 1 bar, at the inlet we don't know. Alright, just now we estimated about 1 bar plus 7 kPa, but maybe not correct. So they broke the pipe into 5 segments. From 5 to 4, they calculated the dPdx there, and then extrapolated for that segment. And then for segment 4, they didn't use 1 kPa, they used the pressure that they calculated from the 3 segment. So the pressure at the 4th segment starts at 106. And then you calculate the 4th segment, all the parameters, and then 3 and 2 and 1 and so on. Alright? You can get, if the pressure, in this case, the pressure doesn't change a lot, it only came from 100, I don't know what, a few kPa only. But if the pressure change is big, then the error could be enormous if you just take one big step. Does that make sense? Alright, so you take in incremental steps going downwards from the point where we do know what the pressure is. Here 1 atmosphere and go down. Alright? So I'll leave you to look at that when you review it. But basically this is what we do lah. Okay. So that's it. I think 2 o'clock already. Okay. Sorry it took a bit longer than expected. I was expecting to finish by 1. I'll see you next Tuesday. So I forgot to announce yesterday afternoon class, but I think I announced yesterday morning and on Wednesday. Our bonus tutorial will be on Wednesday, 9:30 a.m. Room 5001. Right, building 5, the basement, that one. Okay.